Good morning, everybody. So, Doug Walker here. I'd like to iterate what Eric was saying earlier. It's good to be back with you guys. Actually, it was several years before the COVID thing hit since I've been at one of these conferences, so it's really good to be back. So, I'm here from my work from this company called, I'm not supposed to use a laser pointer, but I have to point. So sorry, John. So you can point out. I'm here representing my work office, the Prime Solutions Group. Okay, so they're actually paying for my trip out here. I used to come to these things before. You have to pay them on my own pocket, right? You know, but actually now PSG, Prime Solutions Group, actually paying for the trip, which I appreciate that. So I'll get into the group here, the partnership we got going in a second. So you notice also up here. I've marked out the CubeSat synthetic aperture radar, okay? Because when I first started this, I first wrote the paper in the abstract for the conference back in, I think it was March or whatever. I thought I could believe I could get a CubeSat, a SAR with the synthetic aperture radar on a size of a CubeSat, and I'll explain what a CubeSat is in just a second. But now I'm like, I don't think you can do that, so that's why that's been marked out. So let's go on here. I'll give you some introduction background why we're doing this. This is a different animal, right, than the rest of the conference, right? So I don't have any observation data in here, no telescopes in here. I do have a talk at the end of the program here tomorrow about sending a telescope up. We'll talk about that later. But this is a totally different animal from what we normally hear. But everybody here in the room that's around my age or whatever, remember the Apollo programs, landing on the moon, we're trying to get back to the moon. So I just thought I would do this talk and bring this information for you. So I'll give you an introduction. Why do we need to send something like the SAR to the moon? What is a synthetic aperture radar for folks here in the room that actually have background in that? And I'll get into what we're trying to do with this CubeSat. Now, I've actually probably going to have to be a small sat type system. Project team funding for this. We're actually going after a NASA funding source for this. And then there's actually opportunities. If anybody in the room here wants to go and get involved with this, there's some educational opportunities coming up. So, all right, just a little bit of background. You know, it's been 50 years since Gene Cernan left the moon on Apollo 17, right? And it's been a long time, you know. So we're trying to go back to the moon in the Artemis program. Artemis is the twin sister of Apollo, which is the appropriate name, right? So we're trying to go back to the moon on the Artemis program on the Trump administration's Policy Directive 1. He said we're going to go back to the moon by 2024. We don't think we're going to make 2024, but he put that schedule. There's several, right now we have 3 Artemis launches scheduled. This first one here keeps getting pushed off. Latest I could find was here now back to later part of this coming up in the summer. We'll see if they can actually pull that one off or not. That's an unmanned mission just to test the system out. It's actually going to fly around the moon and circle back to Earth. Artemis 2 is the first manned mission. Okay, so it's scheduled for May 24 time frame, something like that. Of course, all these things are all right. And then lunar landing, 2025. They talk about that, maybe bring the first woman to the moon, first colored person to the moon. So that's there. So 2025 is what we're looking at for actually getting back on the surface of the moon. So Artemis 1 here again is just going to deploy out, circle the moon, come back around, test out the entry vehicle, capsule, and everything like that. The system is basically called the Orion spacecraft. It's actually the capsule that contains the people on board. Space launch system is like the old, what's the new Saturn V, right? Saturn V. So the first test is going to be all these, you know, the launch system, the spacecraft, the ground system, circling around the moon. But also, you know, so they're going to have like these things called a ride share. They're going to take 10 CubeSats along with the Artemis launch to the moon. So a ride share, basically, you know, example, if you've got a launch vehicle that's got 100,000 pound launch capacity, right? Your was 90,000 pound or whatever. You got 10 extra thousand pounds if you can put something up, right? So you can actually apply to do this ride share. NASA has a program to do ride share for CubeSat and stuff into low Earth orbit, and you got some of these things heading for the moon here. Artemis 2 and 3. Artemis 2, I've already talked about this a little bit. It's going to first manned mission here. They're going to circle the moon, come back, and then hopefully Artemis 3 is actual landing here. So some of the targeted landing areas on the lunar surface is these things called permanently shadowed regions. Okay? And actually, most of them are craters and stuff on the moon. Permanently shadowed regions. So there's a reason for them wanting to go there. Okay? And that's one of the reasons that we need a synthetic aperture radar to see down into these permanently shadowed regions here. So why go to these permanently shadowed regions? Well, they think there's water ice in these regions here, okay? And so this has been detected by the Indian spacecraft here back in 2008. NASA actually had a small mini-SAR on that. The Lunar Reconnaissance Orbiter, which was launched in 2009, LRO, it's still up there operating, okay? So it has a SAR on that. And then also the Sophia aircraft, which is the modified 747, having a telescope on board that. That's also try to confirm that there's water ice in the polar regions mainly. So they think that permanently shadowed regions on the moon that don't get any sunlight at all actually has water ice in those regions. Comet impact stuff, they still haven't figured out how they got there. So you'll see articles actually in the paper saying, and you'll see maps like this that show all these regions here that actually have water ice. And if you've got water ice there, that's what you want. Right now you can have a sustainable permanent base there. Right? You don't have to haul that stuff in the Earth, which is just, it would be very difficult to have any kind of presence on the moon without some kind of resources there. So they think there's water ice there. Okay, I think they think it says they are actually confirmed it. Well, maybe not. So it's hard to detect. There's an article right here that says, moon may hold billions of tons of subterranean ice proposed. Right? Science News, and I forgot to put the date on there. It's fairly recent. So, and there's a larger map here of these cratered areas and such. So, the more I've gotten into this, it's kind of like, it's not so confirmed after all, I mean, you read them, again, the news articles and stuff, and at the higher levels, they're saying, we've got it down. Maybe not. So we need a synthetic aperture radar, which actually, and I think I've got a slide come up there, I don't know what that actually is, actually can see into these shadowed areas, but you can't see with optical cameras to try to detect, again, this water ice. And also, if you're going to land in one of these areas, which is dark, right, you really need to know what you're trying to land into, right? You need like detailed maps. So the NASA's science definition report here coming up just a year ago, they're recommending, additional levels of accuracy and precision for surface operations, detailed geological mapping of these candidate sites, similar to Apollo had. So if you remember Apollo 11, when Neil Armstrong was bringing the LIM into land, they had automatic landing system going in and map the area, as well as they could. Well, and he looked out and he was going to land in a boulder field, right? He took over command of the vehicle and flew over that area, almost ran out of fuel, just a few 30 seconds or whatever fuel left, and actually landed in an area that had a boulder. So even though they had detailed maps back then, it wasn't detailed enough, right? And so that was landing in an area where it's visible light and stuff. Now they want to go in these dark areas, and I'm sure the landing vehicles have lights and stuff that light up their area. But still, you want to make sure you're kind of going into where you think that smooth landing areas are. How do you map out these areas? Okay, so one is you think about using a camera system. Okay, here's the camera system on the again the Lunar Reconnaissance Orbiter. They have like a system of 3 cameras mounted on there, okay, high resolution mount. So if you get it down to where, see, here's the Apollo landing, the LIM descent stage sitting there. You got to kind of blow it up real close, right? But you can get details just from the optical cameras, okay? However, if you look here, so there's the optical camera, right? You can say, well, it's darker here. Maybe it's smooth, maybe it's not. And then if you bring out the details, like, well, it's really pretty rugged in there, right? So back to the need for the synthetic aperture radar. So SAR is a type of radar system that actually you're probably familiar with standard radar reflection. Air traffic control, whatever, you send out a pulse, you get a response back, you get a position of vehicle and such. But synthetic aperture radar is you take so synthetic aperture radar, again, is active radar, but you're flying along a path line that's parallel to what you're observing in. And you build up the pulse returns, and you do a lot of complex processing on that. You can actually produce an image with like an optical, radar. And so all this technology has been produced over the years, and actually where I'm working now used to be Lockheed Martin facility, which used to be Doral facility, which started out as Goodyear Aerospace way back in World War II. And in the 1950s, an engineer there at Goodyear Aerospace has the patent for SAR. So SAR was actually invented at the facility I was working at in Westinghouse and Raytheon. So synthetic aperture radar basically is you're flying along a path here and you're mapping out this area. You can produce an image using longer wavelengths of radar, right? So you can see through, from Earth observations, you can see through clouds, you can see it dark. You can actually, I've seen imagery, because a lot of these systems were highly classified that I worked on in the past. So I've been working SAR radar systems since probably 94 or whatever. So. But I've seen actually imagery where they can actually take the radar, bounce it down into a hangar, get the reflection back, and actually put one of these aircraft sitting in a hangar, so from an angle, right? Because it's used for reconnaissance and stuff. So, but you need this for they to look into these permanently shadowed regions. Okay? So they had SARs to the moon previously. So that's one reason, is that you want to produce these detailed maps for landing. Another is in confirmation of these water ice, potentially in these areas, right? Secondary, right? You got a detailed map of the area you're going to land in. You're going to spend, billions of dollars to fly a bunch of people up there, and you have a complex mission, and you land in an area and you find out there's no water ice. So that's not good, right? So how do you determine potential water ice using synthetic aperture radar? It's this thing called surface polarization ratio. So what it's doing is you're measuring the ratio between a reflected SAR-back image from one polarization, like a horizontal versus vertical. So you do a calculation on that, you come up with the CPR ratio, and you get a ratio number greater than about 2, then that's a detection. They say that, there's possibly water ice is in the subsurface and such there because of the way the reflection's coming back. So, but not so fast, right? So the more you dig into this, there's a lot of uncertainty because there's some papers out here that show that some of the radar anomalies are actually due to the surface roughness of the area they're illuminating, right? It's not maybe based on water ice, and it's maybe based on the roughness of the area. So for all those maps of possible water ice, it's still possible, but it's not as certain as they think there is, right? So we need some more confirmations on that. Okay, so what this mission is about is, first started out by saying we're going to put a synthetic aperture radar on a CubeSat, do a ride share, one of the Artemis missions, send it to the moon, energy areas, pin down the detailed maps, confirm water ice. Everybody's happy. Right? CubeSats are a small unit, and it was built up, I think, CubeSats been around for 12, 15 years. They're small type units. One unit is 10 by 10 by 10 centimeters here, and weighs about 1/3 pounds or whatever. So you build these things up by units, and the largest typical units that you do ride shares with now are either a 3 or 6 unit, a 6 CubeSat, And I mean, you've got colleges that built CubeSats in orbit. You've had high schools that have done it right. So there's a lot of organizations doing that. The largest CubeSat that typically that qualifies as a CubeSat is like a 27U type system. Right? So 27 of these things built up. And beyond that, you move from a CubeSat categorization into what we call a small sat. CubeSats going to the moon. Here's just a couple of them that are actually trying to, again, help determine if there's actual water ice on the moon there, right? So you got a thing called Capstone with a flashlight. One is flashlights for Morehouse University. Lunar H map here is with Arizona State University. I'm out of Phoenix, so it's in town here. Actually, I talked to them a couple of years ago about doing program management for the Lunar H map program. So this is going on Artemis 1 launch, right? So they're trying to detect and confirm lunar ice water via these other type techniques, not doing the SAR. So can we get a SAR on a CubeSat? Like I said, when I first started this, I thought, oh yeah, we're put a CubeSat, right? Well, maybe not. There's a lot of commercial vendors now. Just in the last few years, are putting up SAR satellites around the Earth. There's at least 5 or 6 vendors. Here's one of them here called Terra Orbital that are putting up commercial SAR satellites and selling the data for profit, right? For people who want to do like flood control, changes on vegetation, coastal area changes and stuff like that. So the smallest CubeSat or the smallest SAR satellite that I found is the Terra Orbital testing system here, which is about 25K. So if you get a 27 CubeSat, it's around about 45 or 50 kilograms. So this one here is 25 kilograms. You say, well, that one might fit, right? Well, it all now depends on the power, output power of the radar, communication capability, because it's not an Earth orbit, right? You're trying to communicate from the moon. And we're still working this out, right? So here's some of the competitors. Capella Space, so they have a 107 kilogram microsatellite, so they haven't launched that yet, right? Predasar is the one with Terra Orbital. Okay, there's another company called ISI. There's a Finnish company that actually have 18 satellites in orbit. So this is a big business out there now. So you can either go commercial or potentially, Sandia here, Sandia Labs over in Albuquerque. They have a mini SAR that they've built for airborne operations. And that's it's a small size. It could possibly fit on a CubeSat, but it's not made for space applications, right? So a bunch of commercial vendors. So here's Umbra, another one. Eyesight up there. So you got to the satellite itself. But what about getting to the moon, right? It's a hard problem. When I first all this started, and I'll get to the partnership in a minute. I was with the Astronomy Association of Arizona, which now has become a nonprofit. It used to be an astronomy club in the west side of Phoenix. And so I had actually left Phoenix for a few years, came back, and joined the astronomy club. And they asked me, I looked at my credentials and said, well, would you like to be our education director? I said, yeah, I'd like to do that. And I said, well, you're interested in a project? And I go, sure. I said, well, let's send a CubeSat to the moon. And they're like, oh, yeah, they were all excited about it, right? And then the more I looked into it, it's like, so not only you got to get the satellite, you got to get the thing to the moon, right? And so only a couple ways to get there. One is the ride share that I was talking to you earlier about with the Artemis system. Okay, you can't catch a ride to the moon, then you're gonna have to get yourself out of Earth orbit, just like the Apollo mission, right? Out of Earth orbit to the moon, you got to have a lunar transfer vehicle. You got to be able to burn out of lunar orbit. You got to do course corrections on the way. And you got to get into, do another burn to get into lunar orbit, stabilize your lunar orbit. All this time, you got to get position data. Can't use GPS. Lunar orbit's too far away First satellites are using GPS, can't do that in the lunar. So you got to get position data, which comes from the ground tracking system, which NASA has around tracking. You got to get them involved in that, right? And do the communication. So just a big operation to do that. So I'm going to try to do the Artemis ride share. I was looking like, okay, here's the Artemis launches. And so I was trying to put together this proposal, which we've actively got going now. So I actually say, okay, well, what do heck, can you construct them back on the CubeSat? Can you actually construct the CubeSat, get it on the Artemis 2 launch? It's pretty tight, right? If you're going to do Artemis 3, yeah, you got a little more space, but still, these are really tight development programs. Okay, so project team, I've put a team together. Again, I'm Prime Solutions Group. So we do synthetic aperture wavelet processing. So we have the technology to do that. We just recently, this last week, I talked to Lillian Ostrich. She's a physical scientist up at the USGS Astrogeology Science Center up in Flagstaff. So they made all the lunar maps for the Apollo mission. So they're interested in being part of the project and to be generating a more detailed set of for this mission. So got Planetary and Sciences Department up at NAU in Flagstaff. That Professor Mark Salvatore is involved with us there. Dirk Terrell, that was part of the science advisory group here for SAS. He works at the Southwest Research Institute out of Boulder, Colorado. So we have them on board as a team member there. Obviously, they can build a spacecraft. They've sent the New Horizons spacecraft to Pluto, so they'll do that. And then the Astronomy Association of Arizona, again, is this nonprofit organization here where this whole project started from. So the project started with the Astronomy Association of Arizona. We said we're going to send a CubeSat to the moon. Like, oh, that's not going to work, right? And then I was talking to my boss at my work about this potential project. And I said, well, do you want me to try to see if we can pursue it through our company? He was all for it, so that's how it went up. We're actually now working on a proposal due June 15th, so I'll be busy here right when I get back from this. It's a NASA proposal to this Development Advanced Lunar Instrumentation Valley. We've gone back and forth. First, I was trying to put the proposal together to say, okay, we're going to build we're going to take a commercial SAR satellite that one of those commercial vendors produces, do slight modifications as less as possible, put it on a lunar, lunar bus, send it to the moon, do all that stuff. I was going to have Southwest Research build a lunar bus, buy the commercial satellite, put all that together. We'd be doing program management, system engineering, conversations with Dirk. He said, really, this proposal is not really talking about that. It's talking about development of an instrumentation. We backed it off just for the SAR instrumentation itself. So, okay, so opportunities for participation. This we brought the Astronomy Association of Arizona in. They are actually going to do a lot of community outreach with middle school, high school, university, colleges. They do quite a few public astronomy outings and stuff per year. They set telescopes up, bring the public in. So we're promoting this through that public outreach. So if you're interested, like, hey, that sounds kind of interesting, you get piece of action there. Catch me, or you can even email here this general email number there, and we'll get back in touch. Real quick overview of what we're trying to do. Trying to get funding for it. We'll see where we go with this. Right? Now, actually, it was a two-stage proposal we proposed on. I put a stage 1 in. NASA came back and said, please submit, and you're encouraged to submit the phase 2. So we're moving toward that. Yes, that's questions.
Any questions? It's a very interesting presentation. The question that keeps going through my mind is, what kind of budget will this all amount to?
Yes, the typical first year Valley budget, they say it's about $1 million, right? So all we're going to be able to afford with that budget is basically, we're proposing doing the engineering analysis, which will end up with a set of detailed design, basically taken to critical design review. Detailed designs for modifying the commercial spacecraft and looking at the mission requirements for getting it to the lunar moon, and also the SAR processing chain, which we can do there at my work. So I'm quoting in the proposal that, you know, Lunar Reconnaissance Orbiter is a $500 million mission. If you look at the total cost of that, right? Southwest has quoted me, and also it's been backed up by one of the commercial vendors, that you're going to buy the SAR satellite, that's $25 million, right? Okay, so you got to modify that. You know, you got to do the mission operation. If you could do it for $100 million, now you're at 20% less than what the lunar orbiter, right? And we're, I didn't mention this, the resolution levels on the commercial satellites are like half meter to a meter per pixel. The Lunar Reconnaissance Orbiter for SAR was 75 meters per pixel. The best optical they have is a camera with about 1.7 meters per pixel. So we're anticipating we can, you know, a lot higher resolution imagery mapping for 20–25% of the cost of a dedicated mission. That's what I'm trying to sell them. So
hopefully the USGS will end up being a major customer as if this is successful as well, getting a good mapping of the moon.
Yeah, I've tried to pull together team members that would produce that whole chain all the way from the commercial vendors producing the satellite, Southwest Research Institute flying the mission, PSG processing the data. We give the data over to USGS, and they actually can produce the map. So I'm trying to put together a whole partnership and chain that can actually pull us off.
So 2 questions. What frequency or wavelength are you proposing to use, and is it in any way tuned to hydroxyl or resonance potential molecular water?
I'm not. So there's all these different wavelengths. That's one of the analysis portions up front for doing engineering analysis, is to do the mission requirements and see what wavelengths that we need to actually have the SAR satellite generate, and how do we do a better for detection of the water ice. Maybe the commercial satellite's not going to be able to meet the mission requirements. We don't know. That's what the first analysis phase is about.
Other questions?
Thanks. I'm just curious, why radar and not LiDAR?
Well, LiDAR is, you're doing more of a point source type touch and return, and so it would take a lot more orbital passes to actually produce, you know, a mapping of whatever region you're after. The SAR, you could get that in like one pass, you know. I mean, you want to do multiple passes, but you don't have as many orbital passes as you would need for LiDAR. So.
Other questions? No, okay, thank you.